Hello and welcome to online lecture number 14, which is our last lecture for Chemistry 1101 during the spring semester of 2020. In this last lesson, we're going to finish up chapter 10, which has all been about acids and bases. Where we ended the last lesson was looking at how the relative concentrations of hydronium, H3O+, the acid ion, and the hydroxide, OH-, the base ion, how they compare will allow us to determine whether or not the solution is acidic, basic, or neutral. And we can always use that comparison to decide whether a particular solution is acidic, basic, or neutral. But fortunately, there is another more convenient way of expressing whether a solution is acidic, basic, or neutral, as well as describing how acidic, basic, or neutral it is. And that is using the pH scale, which is a convenient way of expressing the molar concentration of hydronium. There's another way of expressing what that number actually is. And the pH scale that most of us are familiar with from other contexts generally goes from 0 to 14. pH can be less than 0, pH can be negative, and pH can be greater than 14. But generally speaking, most substances' pH value falls somewhere in between 0 and 14. Notice that 0 is most acidic and 14 is most basic. So as we go to the extremes of this pH scale, to the far left, at low pH means more acidic, high pH means more basic, the opposite of a basis and acid. And in the middle, we get a neutral solution. So this is a figure, a graphic that kind of illustrates the rough pH, approximate pHs of various substances that we're familiar with. Lemon juice and vinegar, and the stomach acid, I have very low pHs. Black coffee has fairly low pH, whereas on the other side, baking soda, Windex, your ammonia solution, soapy water, bleach, drain cleaner, they tend to have much higher pHs. So these substances in the purple are bases. These substances that are in the greens, the yellows, and the pinks and reds, those are acids. And so this pH says a way of expressing the hydronium concentration, and specifically the pH equals negative log of the hydronium concentration. So if I know the hydronium concentration, then I can plug that into my calculator and find the pH. Notice that this pH scale is a base 10 logarithmic scale. And what that means practically is that a 1 unit difference on the pH scale, so comparing a solution of pH 5 to a pH of 4, means that the pH 4 solution is more acidic than the pH 5. Remember, towards the extremes, lower pH is more acidic, higher pH is less acidic or more basic. So pH 4 is pH 4 is more acidic rather than pH 5. But because there's a difference of 1 unit, and because it's a logarithmic scale, pH 4 is 10 times more acidic than pH 5. Likewise, a pH 5 solution would be 10 times more acidic than a pH 6 solution. And a pH 4 solution would be 10 times 10, or 100 times more acidic than a pH 6 solution. So a small difference in pH actually means a fairly significant difference in the actual hydronium concentration, and so therefore the properties of that substance. And so as we've mentioned, as the hydronium concentration increases, the pH decreases, once again because of the same relationship. So we can then now describe substances as acidic or basic, not just simply based upon the relative concentrations of hydronium hydroxide, but more conveniently based upon its pH. So at room temperature, if the pH is less than 7, then the solution is acidic. The further away from 7 it is, towards 0, the more acidic it's going to be. Conversely, a basic solution is one with a pH greater than 7, and the further away from 7, once again, it's also more basic, then closer to 7, and the pH is equal to 7, then let's say it's a neutral solution. So these three terms all mean the same thing. Acidic means you have more acid ion than base ion, which means the pH is less than 7. A basic solution means you have more base ion than acid ion, which means that the pH is greater than 7. And when you have a neutral solution, so either pure water or even a solution where the pH is neutral, where the hydrogen concentration equals hydroxide concentration, then it turns out the pH is equal to 7. So what we'd like to be able to do is be able to not only, as we saw in the previous lesson, relate hydronium concentrations to hydroxide concentrations, but also be able to calculate the pH given the hydronium concentration and or the hydroxide concentration. So to practice those, we have this one. We're going to calculate the pH of the solution given the hydronium concentration. And then from that pH, decide whether it's neutral, basic, or acidic based upon our criteria. Remember, 7 is our critical number. Less than 7 is acidic. Greater than 7 is basic. And exactly 7 is going to be neutral. We have our two new equations, between hydronium and hydroxide. That product, this product of those two numbers, multiply this number by this number, must equal this number. And then our new equation, the pH equation, pH equals negative log of hydronium concentration. So in this case, we're given the hydronium concentration, and we want to find the pH. Well, to find the pH from hydronium, I just plug that hydronium concentration into my equation. So we have pH equals negative log of the hydronium concentration, which is 5.1 times 10 to the minus 2. So we plug this in our calculator. You should have a log button on your calculator. So it's negative, put in my calculator, negative log of 5.1 times 10 to the minus 2 gives me a pH of 1.29. So that's the answer to the question. If the pH is 1.29, because pH 1.29 is, that number is less than 7, it's our critical number, then we can conclude this is a acidic solution. Fairly highly acidic solution because the pH is fairly low. In our next example, we still want to calculate the pH, but this time we're given the hydroxide concentration of 1.7 times 10 minus 5 molar, and then we ask the same question, is this solution acidic, basic, or neutral? This question is a little bit more difficult because it's going to be a two-step process. We're given the hydroxide concentration and we're asked to find the pH. Notice that pH equals negative log of hydronium, so if I know the hydronium, I can plug that number in, as you saw in the previous question, to calculate pH directly. But I don't know the hydronium, I know the hydroxide. But as we saw in the last lesson, if I know the hydroxide concentration, I know this equation. If I know the hydroxide concentration, I can always calculate the hydronium concentration because the hydronium concentration times the hydroxide must equal 1 times 10 minus 14. So in the first step, I'm going to calculate the hydronium concentration using this equation. It says that the hydronium concentration is equal to 1.0 times 10 to the minus 14 divided by the hydroxide concentration. So then the hydronium concentration is equal to 1 times 10 minus 14 divided by the given hydroxide concentration of 1.7 times 10 to the minus 5. This is identical where we finished with our lesson last time. We have 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 5 gives us a hydronium concentration of about 5.88 times 10 to the minus 10 molar. That's the hydronium concentration. To find the pH, pH equals negative log of hydronium concentration. So therefore, to calculate the pH equals negative log of the hydronium concentration. So negative log of that number we just calculated. We found the pH is equal to negative log of that number, about 9.23. So that's our pH of a solution where the hydroxide concentration is 1.7 times 10 minus 5 molar. Because this pH value is greater than 7, we then have to conclude that this is a basic solution. So you would have properties that would more closely resemble what you expect for a base or an alkaline substance. So now that we know what pH means and how we can calculate it, how can we measure it? So if I'm given a substance, a solution in the lab, how can I tell either exactly or at least approximately what the pH of that solution is? Because remember, pH, even by itself, will tell us a lot about the properties of that substance. So if I want to know exactly what the pH is, I could use a properly calibrated pH meter. That's if I want to know the pH is 5.27 or 5.28, if I need to know that number that precisely. If I don't need to know the number so precisely, I just need to know whether it is acidic or basic, we can use litmus paper, like we saw earlier. The blue to red means it's an acid, red to blue means it's a base. There's other pH paper that gives you more than just simply two colors, where you can use various shades of color, various types of colors to give you at least a approximation as what the pH is. So to see that if it's kind of a greenish color, then the pH is approximately 9. Doesn't tell you whether it's 9.21 or 9.11, but it's approximately 9. Also, you can find something very similar where, so a pH test kit where you can follow the directions, it'll change color, and then based upon that color, that'll give you an idea, an approximate idea as to what the pH of your soil is, and then you can amend it based upon what you're trying to accomplish with your soil. Some plants and bushes and trees like more acidic soils, more basic soils. There's also natural pH ways of determining pH. One of those is with the hydrangea bush. Hydrangea bushes are not as popular around here, but certainly are quite a bit in the south where I'm from. And the actual color of the big blooms these hydrangea bush produces depends upon the pH of the soil. So the pH is relatively acidic, 4.5, you get a deep blue color, whereas it's closer to neutral, more of a deep pink, and somewhere between, you'll get obviously a color somewhere in between. Cabbage juice is a great natural indicator of what the pH is. You make cabbage juice, and then this gives you a range from 2 all the way up to 11, various shades, various different colors that give you an approximation, like this paper would, of what the pH of your unknown solution is. And then even turmeric, which is a pH indicator. Turmeric, it has one color if it's an acid, kind of a yellow color in an acid. It's kind of a hot pink color when exposed to a base. The reason why we spend so much time on pH in this chapter is that pH is very, very important. So not only does it determine the properties of the solution as a whole, but it also largely can determine the chemistry of what's taking place inside the solution. So it could determine the structure of a substance that's present in the solution. For example, this substance, acetic acid at relatively low pH will exist primarily as this substance, whereas at high pH, it will exist as this substance. So different structure, different form, so therefore different properties. It also may determine what happens in a reaction. So this is a reaction where we have these three substances reacting, and at roughly low pH, we get these three products. But the exact same three reactants, but at a high pH, so the same three reactants, at high pH though, give you different products. So in one case, you get this Mn2 plus ion at low pH, but at high pH, you get a completely different product at all, MnO2 solid. So actually what happens in a reaction, at least in some cases, depends upon what the pH is. It may also determine how fast or the speed of a reaction this reaction takes place. And it's at low pH, reaction is very, very fast, whereas at neutral pH or more basic pH, the reaction still takes place, but it's relatively slow. And this is an important reaction because if we are trying to preserve our statues are primarily composed of calcium carbonate, and if they're exposed to the elements, especially acidic rain will speed up this process. So that solid calcium carbonate that statue was composed of will eventually break down to calcium ions, water, and carbon dioxide, and that process will occur much faster, much more quickly when the conditions are acidic. And so because the pH is so very, very important, we want to be able to measure it, either approximately or exactly, and we also want to preserve the pH. We want to keep the pH, in the most circumstances, as constant as possible. Because whether it's an industrial reaction or especially biological reaction, that reaction is most efficient when the pH is a certain value. And if the pH varies too much from that value, either the reaction won't be very efficient or the reaction won't work at all. And if those reactions, especially biologically, are there to keep that person or that animal, that plant alive, then those are very critical reactions. So one way to preserve the pH, keep the pH constant, is to make sure that the reaction takes place in what's called a buffer solution. And a buffer solution is a special solution composed of an acid in its base, and the purpose of a buffer is to resist drastic changes in pH. So for example, a very common buffer that we use in the laboratory might be a buffer composed of acetic acid and the acetate ion. So this is an acid with that acid's base. So if you have this mixture of an acid and its base, and if we add hydroxide ions to this buffer, then the reason why this buffer is able to resist changes, the drastic increase in pH that normally would otherwise occur, is that the hydroxide ions react with the acid that's present and are largely neutralized. And so all we get are water and then a little bit more of this base. So yes, pH does increase, but it only increases very, very slightly. Conversely, if we have the same buffer and we add the acid ions, an acid to this buffer, then the acid ions react with the base that's present. They're largely neutralized to produce water and a little bit more of this acid. And so yes, the pH does decrease, but it only decreases very slightly, not near to the extent that it would if you added the hydronium ion directly to pure water or otherwise an unbuffered solution. So it's very important, especially biologically, and specifically for us, our blood pH, where we have all these different reactions occurring, reactions that would normally produce hydronium ions and add hydronium ions to our system, or other reactions produce hydroxide ions and add hydroxide ions to our system. Even though all that chemistry occurring, we want to keep the pH of our blood as constant as possible. And so part of our blood is various buffer systems, including the bicarbonate buffer, composed of carbonic acid and its base, bicarbonate. And this buffer system, as well as others, keep our normal physiological human blood pH at about 7.4, which you notice is slightly basic, slightly above 7. That's the ideal pH. That's the pH that will maintain, ensure that all those complicated chemical reactions that keep us healthy and alive are able to be efficient and are able to work that they're supposed to. But for various reasons, whether it's usually illness or some other extremes, weather extremes, exposure to elements may affect that human blood pH. And so we want to keep it about 7.4, but the pH drops too much, the patient will suffer from a set of symptoms called acidosis. If the pH drops even further, that might lead to death. Conversely, if the pH rises too much, the patient will suffer from alkalosis. Even further, that would also perhaps lead to death. But fortunately, under most conditions, if we're healthy, our pH is able to maintain 7.4 because of this buffer as well as other buffer components that are part of our biological systems. So with that, that finishes our material for this chapter, and therefore that finishes the material for our entire course.